Okay, so this is a spring 2026 AP Chemistry review session. Thank you for coming. So I've adapted and updated this since last year, don't worry. Here's some general exam information I'm sure you guys already know. This exam is 3 hours and 15 minutes, including your break. It's going to be on May 5th, Tuesday, so you guys have like 3 weeks-ish, um, if I'm correct. And it's going to take place 8 a.m. local time, which sucks, but it's how it goes, I guess. Section one is going to be multiple choice, and section two is going to be free response, and they're actually equally weighted, which isn't typical for AP exams. Um, Usually you see one weighted like more than the other, at least in my experience, but I guess this one is weighted evenly, which is pretty nice because I think the multiple choice section is somewhat easy compared to the free response, so it's good to get like your points in there. Um, And obviously, now all of the questions are going to be provided online, but you're going to like answer your FRQs in a booklet. The thing with the format being online is that I recommend you like always for the multiple choice, even if you're not sure. This is something that you couldn't do when I took it when it was like on paper. Um, if you are not sure about an answer, like it would have been weird to kind of like bubble in an answer you're not sure about and then like have to erase it if you change your mind later. But since you're on Blue Book, it makes it really easy to just like mark down an answer and then you can also flag it for review. And then you can come back and change it without having to like take a time by trying to erase neatly. So that's pretty nice. Um, and just like before we get started, you got this. This is coming from someone who's crime studied for all of her AP exams. I I'm gonna expose myself, but I did not study for any of my AP tests in the past. For like, obviously, I studied for the classes that I was like associated, but I really only studied like the week of the exam, week in advance. So if I can do it, you can do it. And honestly, with the curve, for AP Chem, and you guys are all really qualified chemistry students, so since you only need a 72% to score a 5, estimated, not like exactly, but it's kind of in the ballpark. You should be good, and you've already learned all of the semester content like a while ago, or finished learning, so you should be ready. Moreover, there's a lot of topics that are like considered more challenging that are not going to be on the test. So obviously, there's not going to be any organic chemistry. There's not going to be Lewis acids. There's not going to be phase diagrams. No colligative properties. I'm trying to think of any others. Oh, there's no molecular orbital theory. So you can really like skip over all of those topics, which is pretty nice, and just like focus on the AP curriculum. Something I would recommend doing is there's an AP exam course description if you like go to College Board. And there's like a document, it's kind of meant for teachers, and it has like each topic with like a decimal catalog number. Just go through that. And even easier, you can use like AP Daily if you have access to AP Classroom through like the school that you're taking the exam at. Um, and I just included the curve. So I realized I didn't put like that this is like in like 17.9% go to 5, 28.6% go to 4, etc. But like as you can see, like close to 20-30% scored and then like overall um about mm, like about 40% scored like a 4 or 5. So you have a really good chance. Here's just a quick review of all of the units that the exam is going to cover. So, as you'll see, there's no organic chemistry, as I just said. And even though some of the units look like they might include the topics that I said wouldn't be on the exam, they don't, trust me. I really only put the ones in this list. Like, I'm sure there's more that are not going to be on the test, that aren't in this like brief list, but these are the ones that like I'm, I've never seen on any of the tests. So you should be good. And you also have the calculator and a formula sheet. So you should definitely check out the formula sheet in advance and like cross-reference what formulas you have and are not going to have. If I open this link, do you guys like, and I switch tabs, can you guys see the formula sheet? Or are you still seeing the slides?
Oh, sorry, I was responding in chat, but yes, I can see the formula sheet now.
Okay, sounds good. Okay. So obviously you have the periodic table, and then you're going to have a lot of your most important constants. I can't think of a constant that you're going to need that isn't on here. Like you have Planck's, you have the speed of light, you have Avogadro's, and later you have like ideal gas at STP. You have the integrated rate laws, although they're like in a slightly different form than you saw them in the textbook, but it's still completely usable if you understand like what they mean by like zero and T. They're just meaning the difference in concentration from the beginning to a certain time. You also have a lot of the like equilibrium and acid-base equations. You don't have Henderson-Hasselbalch in base terms, but I don't think you need it. If you can use Henderson-Hasselbalch with like pKb, you can use in pKa because you can just use the other equation to convert it to pKa. But something that isn't on here is how you convert from the equilibrium constant in C to the equilibrium constant in P, which you know is like related to the stoichiometric coefficients. So you should just like review that on your own and remember how to convert just in case it comes up. I don't recall it coming up, but you literally never know. I'm not like a APChem teacher, so this is just like kind of from my experience in my study. Um, and then you have your thermochemistry and electrochemistry equations. Again, I believe this is all you're going to need because you can pretty much derive all of the other equations you need from the ones they give you, especially for like when you get to electrochemistry. Okay, so going back to the main, these are the topics we're going to cover today. So one, we're gonna go over like general tips for the exam, how to read the equation sheet, preparation, and exam tips. But we're also going to go over some very specific topics that are not covered in the OHS chemistry curriculum, or like we don't spend a lot of time with them, or we don't really do like practice questions with them. You might have seen it in Pearson, you may have not. I don't remember seeing some of this stuff in Pearson, which is why when I was studying for the AP Chem exam a week in advance, I was like, oh dang, what's this? So that's why I included it in this. And then also laboratory practices. So this is something that OHS does not prepare you for at all. You will know some basic like terminology for lab equipment just through your at-home labs, but you don't really like know proper lab procedure. So that's something that if you start practicing on your FRQs now, you'll definitely have done later. Um, but yeah, and then also check out my YouTube video series for the gas laws that I made. It's kind of tailored to like the OHS Honors Chem Boot Camp like gas chemistry thing. And I tried to cover every law that you're going to need for the AP exam. Although kinetic molecular theory is obviously separate. I can definitely add a video if you guys want. But I think kinetic molecular theory is not like since it's so conceptual, it's more something that you just read about and kind of apply through multiple choice questions. Um, oh, sorry, I just checked chat for the first time and okay. Yeah, and then okay. So here's some general preparation tips. If you can, my number one tip for the multiple choice section is the AP Daily videos. If you don't have access to them, pirate them. If you can't pirate them, ask a friend that goes to brick and mortar school if they you can like use their AP Daily. It would really help. Obviously, you don't need it to succeed, but I found it helpful just because like it introduces a concept like really fast, like 4 to 8 minutes, and then it goes over a multiple choice question with it, and then goes over the rubric for grading that question. So it's a really good way, like even if you don't watch all of them, to just like kind of get in your head the kinds of answers you need for FRQs or like the kinds of multiple choice questions you're going to run into. And they'll cover any gaps in your knowledge, although I'm hoping that this session is going to serve the same purpose. And you're not going to find past MCQs through College Board like all AP tests. So again, just pirate past exams. There are a lot of people on like Reddit that have like the full past exams, the full official ones before College Board decided to gatekeep them. If you don't want to do that, or you're not able to like find any, or you just prefer like a more structured approach, Khan Academy has some really amazing multiple choice questions, and obviously it can grade it live. I think this is because Khan Academy collaborates with College Board, so they kind of know what the questions look like. Obviously, YouTubers, there's some open source Quizlet sets. And then if you want to use a prep book, prep books are good for like cramming. So if you have barons, honestly, it's kind of hard to cram because it's so in-depth. But I was able to cram the Princeton review. This one's kind of old, actually. This one was from 2017. So when I was studying for it in 2024, some of the info was outdated, but it was still helpful. Um, and oh, actually, no, 2016, so it's even older. But it's really helpful for just like you kind of skim through the pages and you're like, okay, I remember how to do this, I remember how to do this, etc. And you honestly don't have to buy them if you don't want to. You can get it from the library. I bought this like secondhand. Ask your cousins, ask your siblings, ask your friends if they take an AP Chem before. I guarantee you they didn't finish the whole book because most people don't end up finishing the whole book. So there'll definitely be like a practice test they haven't done yet, or it's like no pencil marks, so you can't see what the answers are yet that you can work on. For response questions, grind these into the ground. I would recommend doing at least two. I think doing three is like best. And I think that's honestly enough to see how your answers are going to compare to the rubric. Um, and just make a checklist for yourself. Like make sure you got all the information from the problem and then understand how you're going to approach the problem. Like just make a plan, like just make a fast plan. If you're not really sure, you can come back to it later, but like don't linger obviously on it if you can't think of an approach for too long, just mark it and come back. But even if you can't think of something and you're getting close to the deadline, just like write something in. Like those AP graders are gonna find a way to give you points. They're mostly trying to find a way to give you points, not trying to find ways to take away points. Because that's the way the rubric is written. They're like, you get 1 point if you do this, you get 1 point if you do this, you start from zero. So even getting parts of the problem light is important, and you can talk to Dr. Mel about this because he used to score. This is an AP Chemistry lab manual. Again, this is pirated. It's kind of helpful for understanding like the labs that you do in AP Chem, just like for like titrations and stuff like that. Obviously, the OHS curriculum differs in this way, but if it's helpful for you, I didn't find it super helpful, but some people do. Okay, now I wanted to go over some key lab materials. So obviously you have your beakers, your burners, these are pretty self-explanatory, your safety goggles, but some important ones that you really need to remember what they do because you're gonna get questions as you see later that are about that procedure. So you want to know what a bure is, you want to know what a dropper pipette is, you want to know what a graduated cylinder is, you want to know what a graduated pipette is, you want to know what an Erlenmeyer flask is, you want to know what a Florence flask is, and then, of course, you want to know what a funnel is, and also a pipe bulb, and also a mortar and pestle, honestly, at that. I haven't really seen questions about evaporating dishes recently, but I think that's another thing, like when you have questions or trying to find like the waters of hydration of a certain crystal, that's going to be important. Okay. And this is a list of all the kinds of experimental designs that they'll expect you to know. This is from the 2017 or 2016 Princeton review that I had. So it's kind of outdated. I don't see anything about Beer-Lambert law or gravimetric analysis. And honestly, I haven't seen anything about redox titration in years. I'm pretty sure they removed it from the curriculum. So the main things that you need to know are acid-base titration, component separations, kinetics, and calorimetry. Now, acid-base, kinetics, calorimetry, those are all like kind of woven into the curriculum itself. Like when you learned about thermochemistry, you also learned about like bond calorimeters. When you learned about kinetics, you learned about determining rate laws from experimental data. Acid-base titrations, I'm pretty sure you guys have a titration lab, so you know how it works and you know how to read the graph. But I don't think we had a lab on component separation, so this is pretty helpful. Watch the linked video. I'm not gonna go through it in depth just because like it's a little hard to explain and it's gonna take a while. So just watch the video. I'll send the slides out after so you'll have the link to it since you're not able to click on it right now. Um, but basically the whole idea is that you're separating out a sample using its chemical properties. Usually it'll be like by polarity or miscibility, as you can see. And you'll get questions sometimes that are asking you to like mark up where a like a molecule would end up on your paper. And it's just going to be about the polarity. So like they give you these molecules and you have to explain like why do you think this one's more polar? Why do you think this one's less polar? So obviously you use your brain for that, but then after that, you can just list it out based on what you know about paper chromatography. Okay, that was a lot of yap, but I'm gonna go to our first lab experiment question now. So this is from the 2024 exam, question 7. And question 7 is also the question where you're gonna find your lab lab design kind of stuff. Okay, so you need to list the steps or fill in the steps necessary to prepare 100 milliliters of 0.340 NaCl or salt solution using only the things given, and not all the stuff is going to be used. Do you have any ideas for what the steps would be?
Yeah, I might have an idea. So correct some mass of NaCl on balance, that's already given. Then the next part is to measure out 50 milliliters in the graduated cylinder of distilled water, and then place those 50 milliliters of distilled water in the 100 milliliter volumetric flask. Repeat that twice, and then you have 100 milliliters of distilled
Close,
water.
close. That's where like the function kind of these or understanding the function of these things is going to be really important. So volumetric flask is known for its precision. So if you add stuff in a volumetric flask, you'd know that's 100 milliliters because it's not going to hold anymore. It's not
Ah,
made for
okay.
that. Versus 50 milliliter graduated cylinder, it's not really for like holding things because if you're like mixing up a solution, it's open top, so it's really more for like transferring liquids or solutions between different beakers and stuff like that. Beaker is the least exact. It's more for like mixing things,
Yeah.
but you will find uses for it. So this is the answer. So step 2 would be to combine the salt and some distilled water in the 100 milliliter volumetric flask. So notice how they say some distilled water. They don't say 100 milliliters of distilled water. So this is because you want the salt to dissolve first, and then you get it to 100 milliliters. Because what you don't want happening is like, okay, you have the solid salt, you add 100 milliliters, and then it dissolves. And then suddenly your volume is different because the volume of salt as a solid is different from its volume dissolved. So you want to just dissolve it first, and then you fill it up all the way with water in the fourth step. So really, they're just testing if you know how to use a volumetric flask. And obviously, this is not like a hard procedure, so I wouldn't worry about like understanding how to do really hard stuff. This is pretty standard stuff, pretty standard year to year. Okay, let's try this one. So we want to make a buffer solution this time. Any ideas? Also, Loki gave you guys a hint there. I'll give you a second. Okay, so um well, if we want to have a buffer solution, we want to have both acid and base, right? So our solid CH3 NH3Cl is going to act as our acid, and the aqueous solution is going to kind of act as our base. So we kind of have to use context clues. So step 2 is placing the solid in a 15 milliliter beaker. So presumably we have some amount of solid, and then it says clean the burette, rinse with distilled water. And then there's some intermediate step, and then we use the burette to add 25 milliliters of our base solution to the beaker. So for step 1, presumably we're getting our solid ready. 4, we're doing something to the burette before we can use it to add stuff to the beaker. Um, so if we have 25 milliliters of zero point 0.1 molar CH3 NH2 solution, how many moles do we have? Not all at once, guys. Okay. I got you. I feel you. I'm tired from studying too. Okay, so it's just gonna be a really small amount. Basically, we're gonna have, I think, like 0.0025 mole. So then we just take that amount of mole because we want to have the same amount of acid and base in our solution. And then we use the molar mass of CH3 NH3Cl, which we'll have to calculate ourselves, but you'll be able to do because you have the periodic table. And then you can figure out that you need 0.169 grams of that solid to have the same amount of moles of acid as you have base. And then you'll use the balance to weigh it out. So that's why you have those things. And then for part four, this is like a really niche application, and that's kind of why I wanted to highlight it. You have to rinse the burette with a little bit of your base solution before, because we've already rinsed it with distilled water, but that's before we add the actual amount of base solution that we want. And this is kind of for an obscure reason, but it's just because we don't want water to interfere with our concentrations. And it can mess up with our solution. So this is pretty typical to kind of minimize interactions and stuff like that. Um, but yeah. And since it's such a niche application, I think it just shows that you really just need to do some of these free response questions and then you'll get the gist and you'll see some like you'll learn some like weird facts that they use year to year. I recommend like even if you take like two practice tests and that's like good enough for you on the other topics, just like look through some of the other FRQs at least. You don't even have to do them, but definitely look at some of the other ones for how to do these experimental design questions. Okay. Now moving on to actual conceptual stuff, we have alloys. So I have something about crystal structures here just because it's fun. And if they do mention it, if they show you like a diagram that kind of looks like a crystal structure, they kind of want you, they don't really want you to know the coordination number, the lattice constant. That's outdated information. But or the density, kind of just ignore that top part. But they do want you to know that it's by Coulomb's law and through lattice interactions that ionic solids have such a strong melting point and stuff like that. Because there's a lot of questions where you need to be like, explain, explain, explain. And then for alloys, this is just a little factoid that's definitely going to come up in a multiple choice question. Okay, definitely it's a little harsh. It definitely comes up like every other year as a multiple choice question. But a substitutional alloy, or to start from the beginning, an alloy is obviously a combination of metals. So as you can see in the diagram, you kind of like two kinds of metals. If it's a substitutional alloy, these metals are of a comparable atomic radius versus an interstitial alloy where you have like a very small metal, very large metal. It'll look more like that. Um, you'll either see this as like a qualitative question where you're just looking at the diagram, and it's like, what kind of alloy is this, or what kind of solid is this? And then you could also get it as like they're giving you the atomic radius of these atoms, and they want you to determine if they would compose an interstitial or substitutional alloy. So if there's like a really big disparity, it's probably interstitial. Okay, and of course review your solubility rules. I couldn't find Damelo's original slides because I took this class 2 years ago. But he might have the same slides. Let me know. I'm kind of curious actually. But this is his like kind of chart for remembering, and these are all the solubility rules that you're going to need to remember for the AB test. Honestly, I do remember there was a question where I didn't remember the solubility rules, and I kind of like, I was like, oh dang, because it was a multiple choice question. But it wasn't really like a big problem because like one solubility came up again in the FRQ section. And it was more of a like, oh, calculate the solubility equilibrium. Like it's obviously like they want you to know that like these two things, like this is gonna precipitate out and this thing has to like is gonna dissolve because like it has to be a kind of a switch reaction. Like there wouldn't be a calculation if nothing happened. Versus like for the multiple choice question, I think it was like, is this gonna dissolve? Like what's gonna happen? And I was like, girl, what do I know? But yeah, so just remember these. And I think I wrote on there because there was something that he didn't put. So he said that like silver halogens are gonna be all insoluble. It's actually not true. Silver fluoride is soluble, just not like fluorides are usually soluble in general, just not when they're paired with alkaline earth metals. Okay. Um, Now I had prepared, I was thinking we could go over like the first few units and then we could talk about, because this would kind of correspond to your fall semester topics and we could just like talk about and do like a brain dump of what you guys remember. So for each bullet point that is. So is there anything like from these categories, like any topics that are just like coming to mind? You can do rapid fire in chat because I'm not going to talk while you do this. So I'll have chat open. Okay. Um, okay. It's okay. We don't have to do audience participation today. But yeah, these are just some of the key topics. So some of them are gonna be familiar, some of them are not going to be, but we're gonna pretty much cover all of the ones that you wouldn't remember or you wouldn't know, from across the units. I'm not really gonna review like atomic structure and bonding just because the curriculum is so similar to AP. Obviously, there's gonna be some stuff that you won't need. Like I don't remember de Broglie's law ever being on an AP test. But like otherwise, like you're going to be pretty well prepared for that section as long as you review what you learned in class. But there's some other ones like substances and mixtures and chemical reactions and the other 5 units that are going to be like a little less familiar. Um, and in that case, like I honestly think for thermochemistry, acid-base chemistry, electrochemistry, like the curriculum's already prepared you enough. It's just for some of these more niche topics, and kinetics that we're going to go over. And this is what I was talking about with the explain questions. So one second, sorry, I'm like talking really fast, so my throat is getting dry. Um, On the FRQs, a really popular theme is going to be explain. So these come in all shapes and forms. So sometimes it'll just be like explain this phenomena, and they're not going to specify like the scale, or they're not going to specify the principle they want you to use. Sometimes they're going to refer to the scale. So sometimes they're going to be like use particle level reasoning, use macroscopic reasoning, use na na na. Um, and then sometimes they're going to state the exact laws that they want you to use, like principles of atomic structure and Coulomb's law. And those are really nice because it just gives you a framework to answer very quickly. So, do you guys have any answers for these questions?
Well, I think for the first one, it is either that the molecules increase in complexity, so have more degrees of freedom in that sense, or there are just more the reaction itself produces more molecules, which also increases the degrees of freedom. And I believe that were the two cases covered. There might have been a third.
Hmm. Yeah, perfect. So, that's pretty much it. Yeah, I mean, I didn't include the full question, for part since D is like a part. Um, But yeah, you kind of get the gist. For the explain questions, they do have a specific rubric, and this is another thing that I would recommend. Just go through past AP exam rubrics, like the graded ones, and look at the grading criteria, and see like what they're looking for in the explanations, because you don't want to spend time writing out a whole explanation and find out that because you didn't use like one specific word that they're looking for, that they can't give you credit. Obviously, you don't need to have like the answer they have in there verbatim, but like you need to make sure they're going to explain like what part of the answer they were looking for specifically. Um, and so, for example, using principles of atomic structure and Coulomb's law, explain why silver has a larger atomic radius than copper does. Well, since they gave us two things that they wanted to use, we can assume that there was a two-part rubric. We'll probably get 1 point for using atomic structure, 1 point for using Coulomb's law. So we can say like, silver has a like filled, or it has like an n equals 5 electron shell. while copper only has an n=4 outer electron shell. And since the n=5 electron shell is further out, by Coulomb's law, there's less electrostatic interaction, and i.e. less inner electrostatic attraction between those electrons and the silver's protons. So that's why silver has a larger radius. That's the kind of answer they're looking for. Um, okay, and here's a kinetics overview. Let me check the time. 20 minutes. Okay. We low key still. Why does it say we're on 4? Okay. Yeah, okay. I might have to skip over some of our gas laws practice, but again, you'll have the slides and all the questions since um gas laws are pretty easy once you learn them. And it's more just about doing practice questions, and there's practice questions galore on these slides and also in the video series that I was talking about. Okay, so kinetics overview. So we want to be able to determine reaction order from initial rates. So this is kind of just like setting up your equation. Oh, sorry, I didn't see Avi. Um, Oh, yeah, okay, yeah. Specifically, you can't say like atoms get bigger as you move down the periodic table. They kind of hate that. Like if they give you a specific law they want you to use, like make sure you mention it like in name somehow. Just like integrate it because otherwise like they just can't they don't know that you have like an understanding of how periodic trends work. It's that kind of thing. Just make use of the information they give you in a question, that is. Um, so we have reaction order from initial rates. Finding the units of K based on the reaction rate, and then graphing concentration versus time. So for example, graphing concentration versus time, this is kind of a common knowledge question. For first order plot, uh, we're going to use logarithms. So ln of A versus T is going to be linear. And you would know that just from the integrated rate laws, which are happily provided on the equation sheet, although they're not labeled like zero order, first order, second order. You have to know which one is zero order, first order, second order. The main trick, um, zero order is just going to be a straight line as it is, because the rate doesn't change with concentration. The rate is constant. Meanwhile, first order, you're going to have like a straight line, but varying with logarithm, and it's also going to have a negative slope. And then finally, you have second order, which is going to be like 1 over the concentration, varying with time, but it's gonna go up, if that makes sense. And then for the units of K for a first order reaction rate, we know that our reaction rate should have like moles per second. And if our first order reaction is just dependent on like one thing, so it's like one unit of concentration, so we just have moles. So we have to have K with some units times moles is equal to mole per second. Pretty obviously, the units of K are going to be seconds to the power of -1, so B. Then I'm not going to go over finding the reaction order from the initial rates because it's a little bit longer, but I'm pretty sure you know how to do it. Like you would just want to look like, okay, where do we see that there's a value of OH negative, for example, held constant? So across two reactions, like the concentration of OH negative is 0.030. So you can kind of view it as like we're holding one constant and we saw the other change. So effectively in one, the concentration of ClO2 tripled. And then the the initial rate actually like went up by like a power of 9. So it's gonna indicate that it's a second order reaction, because with triple 3 squared we got increase in 9 in the rate. Um, and then we can repeat the same process for ClO2 since it goes from like 0.020 in 2, but then it's the same in 3. Okay, yippee. So now we also need to use reaction mechanisms, so make sure you remember how to predict rate law using a given mechanism. Um, and also be able to identify intermediates, catalysts, reactions, and products. So, of the proposed mechanism, based on the proposed mechanism, sorry, which of the following is correct? Any ideas?
Well, the first step is the slow step, so it is the rate determining step. So yeah, we would expect uh hmm, which are correct. Oh, actually, one and two only, so B.
Very close. This could just be up to the blurry image, but because we have NO2, F2, yeah, one is wrong. I think Avinash said it in chat.
Oh yeah, so yeah, two is
Yeah.
the only one that's
Um,
yeah.
based on the slow mechanism, since this is an elementary step, we know that the rate law is going to be K times the concentration of NO2 time not squared times the concentration of F2. So it's first order in both NO2 and F2. And that means that 2 is true and 3 is true. So of the answer choices, the correct answer is D. Now, how can we distinguish between intermediates and catalysts?
Intermediates are consumed in the reaction, catalysts are not.
Yeah, perfect. And that's pretty much it. That's like worth three multiple choice questions on its own, at least, that knowledge. So good job. Pat yourself on the back. We also have the Arrhenius equation. I'm not sure if they're going to make use it in its more complex form, but you do have to understand the different like components, um, and like why it works from collision theory, because remember, we're getting molecules to collide, and those collisions also not only need to be like happening, of course, for a reaction to proceed and have enough heat, but like when they're hit, they really need to hit each other because there has to be enough heat. So one, the factors are going to be like, well, what's the frequency that they're colliding? What's the energy of the reaction? Because like, how hard is it to going to be to get them to hit each other hard enough? But then, oh wait, what's the temperature? Because it's going to influence how much energy there is, i.e., how fast the molecules are moving, that kind of thing. So in the Arrhenius equation, which of these constants is a frequency factor? Yeah, if you're referring to A, like the name of the constant, not the answer choice, yeah, it's option choice B, A. And that's because K is obviously our constant, our rate constant. E is going to be like the mathematical E. Um, R is going to be the ideal gas. And then I believe EA is going to be your activation energy. So A is like the um, frequency factor. I think it's also known as the Arrhenius prefactor. That's what it was called in the textbook that we used a couple years ago. Okay. And as I've said already, integrated rate law and half-life, you should know how to do that. You have a sample of radioactive cadmium, half-life of 15 days. If you had a sample that originally weighed 40 grams and then later weighs 2.5 grams, how much time elapsed between the initial and final masses? So it's pretty easy. Just remember, like each half-life that passes is going to have it. Yeah, so we have 40 grams and then we half it as 20, so that's one half-life. We have it again, 10, half it again, 5, half it again, 2.5. So yeah, 60 because we went through four half-lives. This is pretty like if it helps you to write this stuff out on scratch paper, that is like totally go for it. Like even with like
By
determining.
the way, just as a note, it's also assumed that we know radioactivity and it has half um its rate law equation is of a first order. I think that is also good.
Yeah, the thing is, they're not going to ask you about half-life of zero or second order because that's too complex. It's beyond the scope of the curriculum. So if they ask you about half-lives on the AP exam, just assume it's first order. And then reaction energy diagram. Obviously, you guys have seen this a ton of times before, but Can you answer this question 25? Avinash, no, I don't think so. I think you just need to know the 0 point or the natural log of 2 over k equation for um, first order radioactive decay. Yeah, A. And that's the correct answer for 25. So yeah, you guys know what a catalyst is. I'm gonna skip the kinetics practice because my throat hurts. I don't know if I can talk anymore. But obviously, look over this. This is kind of pertinent to what I was saying before. But okay, so gas laws. Are you guys all familiar with the gas laws?
Yep. PV equals nRT.
Yeah, do you know the other ones?
If there are a couple, P divided by V is equal to P divided by V of another one. And then there are a couple of other ones like relating temperature
Yeah.
as well. But it's also just using PV equals nRT, but we use the fact that NR or in some cases T are kept constant. So it's just
Yeah, I
variation.
mean, technically you can derive it from the ideal gas law, but it's honestly easier to just remember like, oh, P over T1 is equal to, or P1 over T1 is equal to P2 over T2, you know? You don't even need to know the name, just remember the relationship because like ideal gas law is good for when you want to quickly like identify like a property of a gas like based on the other ones like if it's static like you're given a gas and you're like okay find the temperature if you have all the other information but if it's like we raise the temperature of this gas like it's really probably only referring to how like oh we raise the temperature of this gas what's the new pressure like it's only going to give you two properties so like ideal gas law is like kind of useless to you then and you do need to know the other relationships which again you can derive from the ideal gas law but it's just faster to know it from like Boyle's Law, Avogadro's Law, that kind of thing. Um, okay, I go over a lot of these questions in the gas video series, so I'm not going to go over those again. But also about gas laws, we have like kinetic molecular theory and like the underlying idea behind gases. Again, this is something that you might have to explain on the AP test. So 39 is actually a very good illustrative question. Which of the following assumptions are valid based on kinetic molecular theory? Actually, all of the assumptions are true. So gas molecules, again, with under kinetic molecular theory, kind of like ideal gases, we're just assuming that gas molecules have negligible volume, you might remember. We're assuming that gas molecules have no attractive forces. Again, this is like kind of like an ideal gas thing. Like you'll see a lot of overlap between what they mean by KMT and real gases. And then really the core part of KMT is that the temperature of a gas is proportional to the kinetic energy, so like the speed of the molecules, which we'll see again with Maxwell-Boltzmann distributions. And then real gases, in which of these cases would a real gas act the most ideal? Yeah, so just wherever we have like low pressure and high temperature, um, so probably D, but yeah. Okay. And we also have root mean square. Um, Usually this is not, you're not going to need to use the root mean square law quantitatively. Like you're not going to use like the square root three, no, no, nothing. Like, no. The main thing you need to know is just that your molecular mass is going to be inversely proportional to your speed. So like the heaviest molecule is going to move the slowest, it's going to diffuse the slowest. Diffuse, effuse, same difference. Actually, wait, fake info. Diffusion and effusion of gases is obviously different, but I just mean that. like it's going to kind of impact the movement in the same way. And then Dalton's pull partial pressure. I really need to get a move on, so I'm going to skip past and then go back to our final topics overview. A Maxwell-Boltzmann distribution. You may or may not have seen this before. I don't think we covered it in OCO1A, but it's a distribution of the number of molecules versus the speed. And that's the number of molecules in a gas. So the two factors that are going to impact it are the temperature and the mass of the gas. So as you can see here. When we increase the temperature of like, say we have a sample of oxygen gas, like it's gonna start, you're gonna have like a high curve that's kind of like with its peak to the lower side. As you increase the temperature, it's going to not only flatten out because we're gonna get more molecules at a higher speed, but it's also going to shift more rightward. And that's like a really important feature of the Maxwell-Boltzmann distribution is that it's not just like moving to the right, like it's flattening. And that would make sense because you have a really wide distribution of particles. Not all gas particles are at the same energy at a certain temperature, even though we kind of like think that with kinetic molecular theory. Because remember, with KMT, we're really only calculating the average speed. That's an average based off like a large distribution. So just remember, Maxwell-Boltzmann distributions, very key. You should go look at it. Um, Mass spectrometry. If you guys took JSO2 at OHS, you might remember what this is. So we have like a relative abundance of certain isotopes, and then you'll get a lot of questions. Usually they just want you to know that like molar mass is not it's an average. Again, it's a weighted average. So if you wanted to calculate the approximate molar mass based on a mass spectrum that they give you, you would just take the weighted average. So you'd have like 28 times 0.9 plus 0.29 times like whatever tiny decimal that they represent. You don't have to do that for this question, which is why the graph is not super easy to read. But you wouldn't. If they actually wanted you to calculate like the approximate molar mass, they'd give you an easier to read graph. And then you can also use it to write the ground state electron configuration, but less relevant. Just know what mass spectrometry is and what it's referring to. Okay, photoelectron spectroscopy. We're just trying to knock out electrons and see what energy they're at. We're going to get intensity corresponding to the number of electrons we knock out, and then we're going to get jumps in energy that are corresponding to a new orbital, and then like you'll get clusters of different peaks, but if you move on to a different cluster, that means we moved on to a different end shell. Okay, so this is actually kind of key, so I'm going to go through both of these practice questions, and then we'll be done. Okay, so number two. Which of the following best explains the relative positioning and intensity of the two S peaks in the following spectra? Okay, I'll just explain it right away. So what do we know? In lithium, we're seeing that the intensity of the peak is a half of what it is for beryllium. So that already gives us some information. And moreover, beryllium has a higher binding energy. So that means that those electrons are being held on stronger in beryllium than they are in lithium. And beryllium also has two more electrons at a certain energy level. So let's look at our periodic table. Lithium, it only has like one valence electron, um, versus beryllium has two, and it has a fully filled subshell. So if we wanted to account for one, that the electrons in beryllium have a higher bonding energy, or like the specific ones that are being studied in this photoelectron spectroscopy. So if we want to account for the fact that they have a higher binding energy, and that there's also more electrons, which answer choice fits that? Okay, drum roll, please. It's A. So it has a greater nuclear charge, which makes sense at this scale, and it also has more electrons than 2s orbital. So as you can see, an important part of solving these problems is just like, okay, we're probably working with the valence. I mean, we shouldn't assume, but like if they don't tell us otherwise, we're working the valence, and that's going to be important for a problem like the next one, which element could be represented by the complete PES spectrum below. Okay, so key features. We noticed that we have we have two clusters of peaks. In the first cluster, we have one peak that is like 1.5 times taller, so it has like a ratio of 3 to 2, 3 to 2 of like lower to slightly higher energy electrons. And then we have the same number of like of the lower from that smaller cluster over here at a much higher binding energy. So remember, we're going to have a higher binding energy at the inner shells. So it's more likely that this first peak is 2 electrons from the 1s2. Moving up, we have the same amount of electrons in another s orbital, and so 2s2. And then next, well, okay, we know that we have 2 electrons because this is a complete PES spectrum, um, meaning that like they completely knocked out all the electrons. Um, so we also must have 2 and a 2s2, okay. And then we have 1.5 times the number of electrons in the next shell up, which would be 2p. So we have 3 electrons, right? In the 2p, so we have 2p3. And the electron or the atom with that electron configuration is nitrogen. Okie dokie. So hopefully this helped like guide your studying and maybe it served as like a test for what you know, what you don't know. Um, Good litmus test. Again, I'm going to reiterate, take at least 2 practice exams. You'll think yourself while you're taking the exam. Um, I've definitely seen people cry in the AV chemistry exam room. The girl next to me was bawling the year I took it. So like, you know, it's okay to be stressed, but like you want to minimize that stress, right? Like you don't want to, I know you guys are all smart and experienced, but you don't want to go into that test feeling like there could be something that you're like, just have never seen before. That's such a bad feeling. It'll stress you out. So between multiple choice questions and free response questions, just remember to read carefully for the multiple choice questions. Answer the question before checking the answer choices so you avoid bias. But if you're not sure, obviously check the answer choices immediately. Do multiple sweeps instead of just spending all your time on one question. And you're not going to get points deducted for wrong answers, so just guess. FRQ, always indicate the particular formula or law that you're using to solve a problem. Like, do not just like show your calculation because they won't give you any credit. Like, if you're using the ideal gas law, write out PV equals nRT before, and then underneath you can plug in your values. But like, you need to write out the mathematical law that you're using first. Um, that is a very key part of the rubric, so you should probably review the rubric on your own. And then here's just a drive that I found of someone who pirated the past FRQs because they're no longer up on the College Board site. But yeah, and this is just all of the resources that I've compiled over the years. So yeah, I hope you guys found this helpful, and you guys can always reach out to me. I'm gonna have office hours like,
Yeah. By the way, sorry for interrupting here. I do have to go now, but thank you so much for this meeting. And
mhm.
by the way, if possible, please uh, mm, post these slides in the AOC chat as well.
Yeah, I am gonna send it out
Ah,
right
okay,
after.
good, good, yeah. So
Yeah.
thank you so much. Bye.
Bye. Okay. Yeah, so my office hours are gonna be 9 a.m. probably on Fridays and then also 9 p.m. But sorry, that's in Central. So I think for you guys, I'd be like 7 a.m. PT and then 7 p.m. PT. I'm just trying to accommodate everyone from different time zones, so I'll be hosting those since it's AP season now. But that's pretty much it. You can find these slides in the pronto, and thanks for coming.